No, yeah, it's not
Feel
mandatory.
free to do. Starts the
Yeah,
broadcasting.
yeah, thanks.
Then you do it.
Yes. So, welcome everybody. It's a great pleasure to start this meetings that will be hosted once every month. This, as Marcelo was also saying before, this is the meeting of the community. So we are really happy to see as many people as possible, and it would be great if this become not only a place where somebody give a talk about his or her research, but also more about discussing, about meeting, maybe making new friends or new collaborators and so on. So we can probably, okay, ideally, probably the idea is that we will have this meeting every third Monday of the month, but we are flexible. Let's say that we will have one meeting per month and then we will see. I also want to announce that soon the organization will become more Latin America because many more people from other areas of Latin America will join. So we will become more international. This is great. And as I was saying, it would be really appreciated if you can send me in the using the email address suggestions for the next speakers, such that I can maybe, let's say, look into people that are not in my, let's say, my standard agenda, and that will be great. We are very happy to have experimental talks, theoretical talks. Also, they don't need to be so closely related. I mean, they must be in the broad quantum community, but not necessarily about technological applications. Today talk will be not about that. So I think we can probably start. So Marcelo Terra Cunha from Unicamp is going to be our first speaker for today. As some of you or many of you already probably know, Marcelo is a professor in Unicamp, and he's, as far as I'm new to Brazil, so I understand that he's a driving force of the quantum community in Brazil. So we started with one of the senior members of the quantum community. So I encourage Marcelo to share the screen, and he can probably start his talk. I don't know, this is a bit up to the speaker. I would tend to encourage people to interrupt and ask questions during the talk, but again, it's up to the speaker to decide if this is comfortable or not. Please, Marcelo, the floor is yours.
Thank you very, very much, Dario, for organizing the thing, for being the driving force upon LAQuA. And thank you, everyone that is joining here. Thank you, people who will see it in YouTube at some moment. And I totally agree that it's much better if it becomes a multiple conversation. So feel free to interrupt me, just entering and making the question,
Yes,
or
not
using
even,
the
yeah,
raised hand if you prefer. And please, Dario, if someone raise hand and I do not be
sure,
aware
I will.
of it, just interrupt me whenever
Sure.
necessary. And okay. So let us start. I do believe that you are seeing my screen with
Very well.
something written like contextuality or non-locality. Take both. You see in the upper part symbols that everyone recognizes because it's written there what the symbol is about. But in the lower part is much better that you see the logo of the International Year of Quantum and the cat that people from SAIFR prepared for the from the outreach part, and it's really a very cute cat. For so I at this moment I have it in my computer and in many other things like this presentation here. And let us start saying what contextuality means, what is it about. So I don't have fear to say that this is the central non-classical characteristic of quantum theory. It's really the good answer for what quantum theory brings that we were not used to before. Having this idea, discovering, creating, then depends on your convictions on how scientific theories appear or are created. So this means the impossibility of making non-contextual models for all quantum probabilities. And of course, I'm just changing words because now what is non-contextual models? And the idea is that the outcomes of measurements cannot directly depend on which other compatible measurements are being jointly measured, or even is not being jointly measured. So remember that one of the novelties of quantum theory is this idea of compatible measurement, or on the contrary, the real novelty is the idea of incompatible measurements. When we just discuss classical stuff, no one asks if two different measurements are compatible because every two measurements are compatible in classical world. So the novelty of quantum theory was the understanding that there are things that are incompatible. However, many things are still compatible. There exist collections of measurements that are compatible. And this is what in our area we like to call different contexts for one given measurement. So a collection of other measurements that are all of them compatible is considered as a context for some measurement. There are two types of contextuality, or two types of quantum contextuality. One that we call state-dependent contextuality, and the name already says it means that you can choose states where this failure of classical description appear, this impossibility of having non-contextual models manifest itself. And even more surprising, there is the notion, there are examples of state-independent contextuality. And when we say this, we really say for all states, including the most mixed one. And probably, if you think a little bit, it's hard to believe in it. I remember my first times, I was really struggling against it. That, come on, the most mixed things, you just have equiprobable stuff for every measurement. And I said, no, you really can have state-independent contextuality, something that I will not talk about during this lecture unless you ask something about it. But this kind of question, I prefer that you wait upon the end if you really want to know something about. But I will show interesting stuff about state-dependent contextuality. So one historical milestone, and in a minute a disclaimer is important to say. So I'm talking about what we call Koch-Specker contextuality. There are also different notions of contextuality. We can extend the notion of contextuality, but for this talk I will focus on Koch-Specker contextuality. That is the one that I'm already talking about, the impossibility of making models for non-contextual models for obtaining the same probabilities as a quantum system could foresee. Okay, and the disclaimer I already made. During all this talk, I'll only talk about this kind of contextuality, Koch-Specker one. Okay, this is a picture that appeared in the original proof, a graph. In this graph, you can see 120 vertices. There are some, and these vertices represent measurements in a spin one system, as they would call. Nowadays, we would call a Kiltridge system, but it's the same stuff. A system whose state space has 3 dimensions. And this means that whenever you have a triangle, one and only one of the outcomes should appear. While when you have just an edge, it means that not both can appear at the same time. So it's an exclusivity graph, as we like to call. And it was not the name at that time. It was just a drawing that they were making for people to understand what they were proving. I will not discuss their proof, again, unless someone asks. It's not difficult, it's just 2 or 3 steps to understand what they were showing, but they were showing a state-independent proof of contextuality and already using the notion, even if without this name, of an exclusivity graph. You can see that this beautiful 8-vertex graph repeats itself 15 times in this picture. So it now became famous as the bug of Koch and Specker. So essentially, the proof depends a lot on this specific bug and dimensionality, as I already mentioned, the idea that it's a three-dimensional system. And this brings the idea that whenever you have a triangle and you see that the bug has exactly two triangles and two pentagons, this is the idea. These triangles obey the situation that one of the three should appear. So in the end, it's a kind of coloring vertices with only two colors and the rule that whenever you have an edge, you cannot use one of the colors. So it's easier to consider that it's a yes or no thing, and you cannot have two yes connected by an edge. And whenever you have a triangle, you have to have one yes and two no's. So this is how their demonstration worked, and I already said it's an example of a state-independent proof, and that's why they need that many events, that many vertices. So they were really considering the situation of no possible choice of quantum system will, in three dimensions, will allow a graph, an exclusivity graph like this.
So, for instance, the famous, let's say, Bell thing is a state-dependent contextuality, right?
Exactly.
Okay. Okay.
Whenever we go to non-locality, it's one example, it's a huge class of examples of state-dependent contextuality. That's
Okay.
a good point, and I will come to
Mhm.
it later. So the beautiful thing, so this is just another way of drawing the things, and now whenever you have a line, everything is compatible with everything. So, and the line can be a straight line or a circle. So this is the understanding of this way of drawing graphs in a different way. So for those that already understand the drawing, then it becomes easier to recognize things, but not necessarily all the time. But the important thing is that exclusivity graphs, when we go to quantum theory, this demands that orthogonal representations of this graph should be implemented. So you need vectors that whenever they are, the corresponding vertices are connected, they have to be orthogonal. And this is what people in graph theory will call an orthogonality, an orthogonal representation of the graph. Now, an example of state-dependent contextuality. The simplest example of state-dependent contextuality is what we call KCBS, the name of the four guys that give the origin of KCBS acronym is in the upper part of the slide. Kliashko, Ken, Bonicioglu, and Shumovsky. You don't need to learn how to pronunciate all their names, just KCBS, everyone will recognize. So you have this pentagonal compatibility structure. In this sense, every measurement, we only have 5 possible measurements, and each of them is compatible with 2 other and non-compatible with the other 2. So pay attention that I'm changing the meaning of the graph at this moment. I'm now considering as a compatibility graph. I'm describing the scenario that I'm working. And I will consider the situation where those measurements are dichotomic, each of them, and I will label as plus and minus 1 the possible outcomes. It's not that important which are the outcomes. I will mention the advantages, but it's essential that we consider dichotomic measurements, only 2 possible answers. And if we insist in trying non-contextual assignments, we'll be able to prove an inequality that can be written in this way, and we can, choosing the plus and minus 1 labeling, consider that what we are writing here for each of those correlators that I will interpret in a different way later on. But here you can consider this as just the product. So if you have both of them with equal sign, it will give a plus 1. If they have opposite signs, it will give a -1. So each of these guys here is an expected value that ranges from -1 to 1. And you see that this minus sign here is essential for saying that whenever you try to make a classical description of this thing, you try to answer all the questions, you try to assign values to each of the 5 of the guys, you have a bound like this. You cannot go above 3 with this linear combination of 5 terms, each of them varying from -1 to 1. And of course, the beautiful part is that with quantum theory, you can choose 5 different dichotomic measurements and 1 quantum state and obtain a value that's much larger. It's this beautiful number here that is approximately 3.94, much more than 3. So you are violating what we call a non-contextuality inequality. That's just the friend, the cousin of the Bell inequalities. So Bell inequalities are the example of this when the scenario that we are working is separable. Is something that you put some of the measurements for one player, some of the measurements for other player, every measurement from here compatible with every measurement from there. This is a bipartite Bell scenario, but we will arrive to it.
Sorry, what is the let's say this is came much later than Bell. So what was the how can I say the great achievement?
Motivation.
What do I learn much better? What is okay? Let me say it this way. What is more surprising than just Bell from this?
Okay. One thing is that Bell always gives the impression that entanglement is the central issue. And here you cannot even talk about entanglement. You
I see.
can obtain this violation in a three-dimensional subsystem. So there is not even a way of saying separate this as a tensor product of this and that. No, it's
I see.
just
Okay.
one system. So this is what
Oops. Uh, is my problem or everybody lost connection with Marcelo? Can somebody? Ah, okay. So it's only, cioè, it's not my problem. It's a problem of Marcelo, right? Do you confirm that you can hear me? Okay, good. So let's wait for him to reconnect. Okay, yeah, yeah. Let's wait for a sec. Okay. Now you are still mute, Marcelo.
now you
Okay,
can hear
great.
me again.
Yes.
I have no clue if the problem came from here, from
Yeah,
elsewhere,
here
or
we were still discussing among us, so apparently you were
so that's my
disconnected.
fault.
Yes.
Probably because we were touching something very important. And the something very important was that comment that to some sense we became too fond of entanglement.
Oh, I see.
When we only see things as Bell inequalities are the most important thing to say what quantum theory brings of novelty, then for violating a Bell inequality, we do need to have need to have entanglement
I
in the
see.
state that we use. So this is one of the important
Okay,
generalizations.
thanks.
And then to some sense, 3 dimensions is the minimum that you need in order to have some non-classical thing with projective measurements, we have to say. And in the same way, just 5 measurements is a very small number, but okay, in Bell you only have 4, so in some sense it's in CHSH you only have 4, so this is not the real minimum in any sense. But okay, so thank you for the question. It's a
Yeah.
good thing for making clear. And of course, we like to joke that one of the mottos that we use is let Alice and Bob play together. This is what they do in contextuality, that you do not need to separate things. Of course, the price that you pay is that you have to justify somehow compatibility and or incompatibility among the measurements. Incompatibility is easier to prove because then you can have some inequalities and etc. But compatibility itself is a kind of loophole. It's somehow something that you need to assume, or at least you can only prove that you are not contradicting anything that could be consistent with compatibility. And
But for
this,
instance, suppose that this three-level system is a spin-1 system, right? That could be one example. So
yeah,
can you give an example of what are these five measurements that are that have this compatibility structure?
it's all in the sense that one of, so I will need to find exactly five vectors to
Mhm.
say that each of them is attached to one of the five measures plus one. And the other plane, the orthogonal results,
Mhm.
will be related to the minus one. So these
Okay,
five,
because I mean, I don't know if this is just my problem or can be also for others. Cioè, when we talk about, for example, two-level systems, I say, okay, I measure the spin in a certain direction. Do you have something of this kind in this scenario? Like you measure the spin in some, is it something that can go to that? Oh, we lost him again. Yeah, same as before, right? Everybody is with me, and yeah, it's okay, great.
here am I again, sorry, once again. But okay, you were complaining that with qubits you can always understand the
No,
measurements.
but I can also understand with spin 1. I mean, measure the spin and I get, but I wanted to understand what if there is a simple way to see these five measurements, like spinning, I measure in one direction, one other, or.
Remember that not all measurements for a three-dimensional system is a spin in some direction, because with a
Mhm.
spin in some direction we would have a trichotomic thing,
Mhm.
and with the
Right,
trichotomic
right, right.
things become harder because it's a complete
Mhm.
measurement. So,
Okay,
but of course we could consider the square of it, and
okay.
it is already something that just
Mhm.
define one
Sure.
direction to be the zero and the complement of it as a one.
Right.
But it's easier just to forget about the spin and go to some other three-dimensional system, like
Mhm.
a three paths in an interferometer or something
Okay.
like this. And then,
Okay.
if you
Mhm.
can play in these three dimensions, it's always related to define one vector to be the direction of the plus one, and the
Mhm.
orthogonal plane to be related to the minus one.
Okay.
Okay? And
Okay.
then it's very beautiful that the maximal violation here, this value of 4 square root of 5 plus minus 5, it comes from a construction that was already known in graph theory.
Mhm.
So just repeat the question 2 or 3 slides later on, that I will say, okay, here is where we learned the connection of those two things.
Okay.
Okay? So we already said it's a state-dependent proof, and now graph approach. Now things that
Mhm.
people already knew in graph theory that at some moment could be recognized by these three guys, that is very related to quantum theory, even if up until 2009 when they started to discuss, and 2010 was the archive that mentioned there. No one else was aware of this connection. So you see that we can rewrite those inequalities. I will be more clear in the Bell example later on. But if we can write an inequality of this kind, so for this case of KCBS, you are just summing in the vertices of a pentagon 5 possible things, each of them with some probability. So again, if we define for each direction, if of each vertex a direction to be the plus signal, the plus one outcome, then whenever we discuss the probability of that outcome, it will become a probability P for the thing associated to that vertex. And we can rewrite the inequality and understand this KCBS of the plus minus that. Right? We can rewrite it as this sum of 5 terms, non-contextual, with non-contextual models, never going beyond 2. And this 2 is very classically understandable, that if now we go for a pentagon of exclusivity, you can take 2 vertices that are not connected and say, okay, I will give yes and yes for those 2 guys, and the other 3 have to be no. And then every non-contextual model will be a convex combination of choices of 1, 2, or even 0 yes, and this can never have more than 2 yes. So this is the central the way of understanding this. This is square root of 5. Remember that in the previous slide it was 4 square root of 5 minus 5. So this square root of 5 is really related to your concern. Can I have a way of visualizing this measurement? And yes, you can. So those things, so this is what quantum theory or quantum mechanics allow us to go. And if we go to the more general picture that only say, okay, whenever those 2 guys are connected, the sum of the probabilities cannot be more than 1. Then you can imagine a situation with a more general theory that gives you 1/2 probability for each vertex of the pentagon. You just obey this exclusivity condition of no more than 1 if the things are all connected, and in the pentagon the all is just a pair of them is connected, and then you can go to these 5 halves. So there is a question here, if the no signal bound in between, it's not exactly non-signaling, because here we are just discussing in one system. So there is something related to non-signaling that we call non-disturbing, but yes, you can obey non-disturbance and obtain this 5/2. So, and it's not precisely nor non-signaling nor non-disturbing that really gives this outer guy, but it's a very good question, Herbert. Thank you, and sorry to make you explain, but surprises are good. Surprises are always the things that make us learn more. And okay, so more generally than the pentagon, if you have an exclusivity graph, so and you write this inequality, that is the sum of the probabilities that are being assigned. If you make 3 different models of how to assign probabilities, the first of them, non-contextuality, so the first of them, just consider that every question has an answer, and now just make convex combinations of those things. You never go beyond this number that was already named, the independence number of the graph. So this alpha G is just independence number. If we go to the extreme opposite situation, the alpha star is just obeying that whenever you have a click, oh, this means many vertices when all of them are connected 2 by 2, Then you impose that the sum of those probabilities cannot be more than one. This gives what is known as the fractional packing number. And the beautiful part of quantum is that Lovász had already invented a way of calculating what we call Lovász number or the Lovász theta function of a graph. And the idea to calculate Lovász number is orthogonal representations of the graph. You just choose for every vertex a vector with the rule that if the vertex are connected, if there is an edge, then these vectors have to be orthogonal. In some cases, it's the opposite. If it's the absence of an edge, then you demand orthogonality. This has historical reasons and etc. But let us focus on orthogonality whenever you have an edge. And then you choose some other vector of the same vector space with all vectors normalized for the graph, for the vertices, and for this extra one that we call the handle. And now you do modulus square of the inner product of those guys. This is the probability in our interpretation. So you are just summing this thing. So Lovász already defined it as this sum of the modulus square of each of those inner products. And of course, when we quantum say square of an inner product, we interpret this as probability of a result. So this was quite a coincidence that Lovász was already using this thing, and decades after, essentially Simone Severini was the one to make this connection and discuss with Sadan and Andreas, and they three became the fathers of this graph approach to Kochen-Specker contextuality. So the idea is that now we can go back to Lovász, who the first non-trivial example that he made was for the pentagon.
Okay, usual break. This is probably, we can say that is our, let's say, our version of a coffee break. It's very, let's say, we have a coffee break every 10 minutes, but yeah, hopefully things will. Oh, you tried to change the room? Apparently, still have some issue. Let's see. It's funny because we stayed like 10 minutes before the talk, chatting randomly, and apparently everything was perfect. But yeah, unfortunately, this is probably. Yeah, Marcelo, we were saying that we are facing a sort of Murphy. Exactly. Another example of Murphy law. We stayed like more than 10 minutes chatting about random stuff and everything was perfect. The moment that the talk start, everything is fuck up. But yeah, this is life.
Fantastic.
Okay, let's go ahead.
Yes, I changed my place to see
Yes,
if
I saw.
the,
Maybe this is better. Yes.
exactly. And so I'm trying to make you imagine now that we have this star-shaped pentagon.
You're not sharing the screen right now, eh?
No, I'm not. I'm just
Okay.
using my hands here for you
Mhm.
to see. And now if you take two neighbors in this configuration, so, and take the vector that comes from the center of the pentagon to the vertex, they will have a 2 pi over 5 angle. And this is more than pi over 2. So now you consider that you are not anymore in 2 dimensions, but in 3 dimensions. And you put a small component here that you start growing it. So instead of keeping these guys here, they are raising. And you see for continuity that the angle is coming smaller, and there is a precise size that you put here in the third dimension that makes them orthogonal. And for symmetry, you have orthogonality not only of those two, but any two neighbors in the pentagon.
Sure.
So you have those five vectors that you start with the projection in the plane. Now you put the same part in the third axis, and you have five vectors that obey the orthogonality of the pentagon. And even better, the handle, that's the reason of the name. The Lovas considered that you were playing like an umbrella. So you have these things of a pentagonal umbrella, and the handle of the umbrella, because it's really in this third dimension, the guy that is the z direction. And then you see that the proper size is exactly 1 over square root of 5 for all of them to become orthogonal. And when you square, it's 1 over 5. And when you sum all of them, okay, sorry, it's not 1 of square root of 5, it's 1 of the fourth square of 5. When you square, it becomes 1 over square root of 5. When you sum 5 over square root of 5,
Yeah, it's a very unfortunate situation. Mm. Welcome back. You are mute. And we lost again. Yeah, we... Okay, let's see. Let's try to unmute first. Okay.
exactly. It's dangerous that the change of place makes even things worse.
Yes, exactly. Yeah.
Okay, let
You
us.
don't have a wired connection, right? Often that is more
No,
stable. Unfortunately not. Yes.
exactly. I would need an adapter because I can have the cable there, but I
Mm,
do not have how
I
to
see.
plug in the.
Yeah. Okay,
Okay.
let's try to go ahead.
And here we are once again. So remember that I was discussing numbers here. Now I change to sets. And those sets are exactly the sets in this interesting space where we put the numbers, the probabilities. Each P of VI will be one entry of these vectors. So that's why you have this R to the V, the vertices of the graph. And this is the set that you obtain when you are calculating the stability number, the alpha number. This is optimizing the sum in this stab set. When you are calculating the theta number, you are optimizing the sum in the theta body, as it's called. And when you are calculating alpha star, you are optimizing the same linear function in this polytope, this Q stab. So those were already
Mhm.
known sets in combinatorics, in graph theory, and they could be directly related to non-contextual set of correlations in a discussion of foundations of quantum. The quantum set itself, in the sense that you can find a quantum system that realizes those exclusivities, and you can obtain every behavior that is in this interesting set. And finally, this exclusivity, I will not enter in the detail of the one. If you want, I can say in the end.
Mhm.
And finally, let us come to non-locality. So How is the most usual notion of non-locality? You are used to the idea of two parts. So Alice and Bob, they want to make their communications and etc. They want to see strange correlations that can appear. The usual description is like this: these black boxes where you enter with some choice of input that in physics will be considered as a choice of measurement. You receive the output or the outcomes of the measurements that were chosen. And to describe an experiment where you repeat many times those things, you have this thing that we call a behavior, this set of conditional joint probabilities. Given the choices x and y, I will describe this probability of outputs A and B respectively. So the simplest example, Clauser-Horn Chamonix Hode, and for this case, every alphabet is dichotomic, and for example, use 0 and 1. And then you come to this most famous form of the CHSH inequality. But if we want to have this form and the labels are 0 and 1, we have to give a different definition of such a correlator. And I mentioned this before. The definition can be made like this. And what's the beauty here? That we are discussing everything in terms of the probabilities, not the specific labels that we choose for the outcomes. So if they agree, you just subtract the probability of agreeing and disagreeing. So this makes this number again vary from -1 to 1 if they always
Sorry,
disagree.
on the second, it's a typo, right? It's not x times y, it's x comma
Oh,
y.
sorry,
Right.
sorry. Yes,
Okay,
yes.
great. Yes,
A
yes, yes.
comma, like just like here. Yes, thank you.
Sure, sure,
Sorry.
sure.
And so this guy, so the x and y is the choice of measurements for each of them, and we are just making this difference of the probability of agreeing the results, the outcomes, and the probability of disagreeing. So if they every time disagree, this is -1. If they every time agree, it's +1, and in general, it's some number in between. And the usual CHSH inequality, this minus sign here makes this thing not more than 2 if you do a local model. And a local model can be translated in this expression here, where for each choice of lambda, the probability of the result A can only depend on X, the part of Alice. In the same way, the probability of the outcome B can only depend on Y for each choice of lambda. And then
And lambda is in this framework, lambda is
we can interpret just as something that you are using for making convex combination. So you are making convex combinations of things that only depends on their own lab.
I see.
And that's also what people like to call hidden variable. I don't think it's a good idea. I think we give opportunity for people to think in strange things instead of just mathematically describing this as a model. It's simply for each
So,
choice of
okay.
lambda, things work. Okay?
Okay.
So
Okay.
you see that if we define lambda, then I'm considering independent behaviors of part A and part B. So lambda is responsible for the correlations.
Yes.
And that's how we describe classically the correlations of two variables or two laboratories or whatever. We put this extra guide that can be called a latent variable. It's another interesting name, much better than hidden. It's just something that we are not verifying. We do not, it's not something that comes from a conspiracy or whatever.
So, for instance, for Alice, lambda will be the result that she cannot measure of what Bob measures, so to say. And
see that lambda needs to be in both of them. So
Exactly.
another interesting name is shared randomness.
Okay. Yes, exactly. Exactly. Yes, 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 yes.
Something that is available for both, even
Yeah.
if they do not read, even if they do not
Yeah, it's
record it.
yeah. It's this idea that they have these two languages. I mean, there is this idea that there is a randomness, but yeah, it's shared. So okay, got
Exactly.
it.
It's
Yeah,
something
okay.
that usually we consider as related to the common past of them.
Correct, correct. Yes.
They established this somehow,
Mm-hmm.
and essentially, a quantum violation is saying that classical models for the shared randomness is not sufficient. You need to consider
Great.
that this past really gave you entangled states that then measurements
Mm-hmm.
will happen in each side, and
Mm-hmm.
one of the consequences that we are not able to have outcomes previously defined instead of consider that they only appeared whenever you measure. So
Mm-hmm.
this is the central point. And as we have already mentioned that the pentagonal thing can have one form in terms of correlators and another form in terms of sums of probabilities, the same will happen here. We can rewrite this same inequality essentially. You see that here we are only considering for the choices 0 and 0 for x and y, the cases that agree. So the positive part here of this correlator. The same thing for the second term that involves choices 0 and 1. The same thing for the choices 1 and 0. And the opposite here, because here we have the minus sign in the inequality. And remember that this sum, since this probability are normalized, you can always write this guy here as 1 minus the other one. So this is the way of passing from this expression to this expression. They are totally equivalent. But you see that I included the letter G here that you can imagine from where it came from. We are just imposing for this example the same idea of a graph description given by Cabello Severini Winter. So this will be the graph related to this inequality. So you see that these 8 probabilities here, these 8 events, each of them we are as prescribing some probability, can be included in a graph like this. I will not give the details, I'll just label them here to be a little bit faster and see that this central point is not a vertex and it's just a crossing of edges. We have this 8 vertex thing and we can apply Cabello-Severini-Winter theory for it. And this number 3 here, remember, comes from the independence number, comes from the maximum number of vertices that we can find that are not connected, any of them. So here you have one example of a choice of 3 vertices, but the important part is that you can never have more than 3. If you try more than 3, you spend the rest of your life trying and you're not be able to. Of course, you can prove that you cannot have 4 of them, and it's quite easy for this case. Naturally, whenever you talk about Bell inequalities in these times, we have to honor these 3 guys that received their Nobel Prize for it. But let us insist a little bit more in this idea of relating the CHS, the Cabello-Severini-Winter, the CSW approach, to CHSH, to Clauser-Horn-Shimony-Hold. So you see that here we can call the local set, the set of things that can be classically described, and this is exactly equal to the stab set of this graph that we just shown. And Cabello-Severini-Winter would say that, okay, quantum theory will be related to the theta body of some graph or of some realization of that specific graph. But here we need to go a little bit further because I started from CHSH inequality. I showed to you how the graph is, and this is the the way the if I just reprint here the graph. But I have an important question for you. Can you see Alice and Bob in such a graph? And the answer is no. We don't have anything to say which thing is really related to Alice and Bob. We don't have this bipartition really manifest in such a graph. But if we do just a trick and we color the edges, so you see that in the outer part here, I'm alternating the colors, red and blue, but here I'm using double colored edges. So all of them are both blue and red. And here we can say each color is related to one of the players, one of the labs, and the exclusivities that are the essential part of such a graph. Now I can say that here, if we like to say that Alice prefers the red, so here Alice is seeing this orthogonality of or the exclusivity of 1 and 2. She's also seeing the exclusivity from 1 and 5, in the same way from 5 and 6, and 6 and 2. This red thing here gives us this piece of 4 vertices, in the same way as the other piece, 7, 8, then 4, and in the next slide I can be more detailed about it. So those are the red cycles of size 4 that you can see here, 1, 2, 6, 5, 1, 2, 6, 5. The same way for this other square, this 7, 8, 4, 3, 7, 8, 4, 3. But in blue, you see the other situations, the 1, 8, 4, 5, 1, 8, 4, 5, and the 2, 3, 7, 6, 2, 3, 7, 6. And you see that this already labels to us all the measurements and the exclusivities that are appearing. So we can put the label 0 in red here and 1 in red here for each of those pieces. And you see that this piece, this 0, only need to say that 1 is exclusive to 2 and 5, in the same way as 6 is exclusive to 2 and 5. So you see that you can use the same label for the output for 1 and 6 for this question 0 in red, in the same way that you can use the same label for 2 and 5, and you explain all those exclusivities here. So you essentially re-obtain all the information that is written in this inequality, just drawing and coloring these edges in this way. So that's why I'm removing here the inequality to say the inequality is already written in this colored graph, not only with the bound tree that was also present in the black graph, but also saying that we have two parts because we used two colors, and how many questions I'm making in each part, and the outcomes. Of course, I can relabel them as I wish, but I know that this structure here is only consistent with the idea that the outputs of 1 and 6 for the question 0 are the same. And this is why 1 and 6 are not connected at all, but especially they are not connected in this red square. The same for 2 and 5 and all things that are included here. Okay? So this is what is described in this paper here. And there we also describe other examples, other famous examples, like what we call pentagonal Bell inequalities. And you see that this kind of pentagonal Bell inequality, we have a double edge here, and this is essentially included in the previous example. You just forget about these numbers 6, 7, and 8 here. You just consider these 5 events numbered 1, 2, 3, 4, 5, their exclusivities, and this brings this kind of pentagonal inequality here with pentagonal because we have 5 terms. The exclusivities really make a pentagon as in the previous case. And this bound now is 2. And with quantum theory, you can go up to this number here, this 2.178. But we have another interesting pentagonal inequality that is essentially obtained by removing one of the colors here. So we have this other thing that is another pentagonal inequality. In the original paper that mentioned in pentagonal inequalities, 2 of them were written, but we understand them as the same, just realized in different scenarios. And the bound, the quantum bound, is a little bit above the previous one, which makes all the sense because we are demanding one restriction less. We are imposing just one orthogonality here, while in the previous one we had a kind of double orthogonality. But since the first moment we were very concerned with the interesting fact that for CHSH we have this agreement, this coincidence of the usual theta function and what we call the colored theta function. So both of them come to this interesting value 2 plus square root of 2. And then we started with the question, okay, but what about the behaviors? This maximal number is the same, but is it true that you are optimizing in the same set, that every behavior that can be obtained from the colored graph will be obtained in the non-colored one? This question, the answer is yes, but the important question is the opposite. Everything that I can obtain with the uncolored version can be also obtained using the colored one, can also be obtained in the CHSH scenario, when you really have 2 players playing, each of them with just part of the questions. And the answer was obtained during the master work of Lina van Dre. The answer is no. We can have the set is really larger, the black set, what we can now call the non-contextual set of the CHSH graph, or what we simply call the shadow graph. This is the case that cannot be, that is larger, and the bell part is a little bit smaller. But okay, I have to run a little bit if I don't want to take all your afternoon. So what about the building blocks for quantum contextuality? We understand after this graph approach that the cycles of odd size are very important. The pentagon is the first important example, and then heptagons, etc., and their complements are the important case. And we were asking, can we have this coincidence of theta and colored theta be the same also for those building blocks? And the answer is no. It was also a master student who could prove this, Lucas Porto, that nowadays Lina is already a doctor, that she finished her PhD in Siegen, and Lucas Porto just started his PhD in Sorbonne, and he could answer that no, or as I'm joking there, or probably not, in the sense that for the cycles, it's really no. For the complements, we could only prove up until a large number of vertices, but not, or we don't have a complete demonstration yet. And one incident part is that you can ask for a colored graph, a graph that the edges are colored, if they can be realized in a bell scenario, in this way of, okay, take for each color one part, and for each part just one measurement for each vertex, and try to recognize it as a bell thing. And we could work it out to understand that this is the easiest way of making exclusivities. If you have just an exclusivity like this, one dichotomic measurement is enough. If you, and 0, 1 as good labels for the outputs, if you have something like this, a path of size 3, you can do as we organize it here, as again, just 2 labels are enough. You put 0 for both extremes and 1 for the center, and this is a labeling. Here is what appeared in the CHSH case. The squares that were there can be understood as these. Two of them are 0, two of them are 1, and the connections are like this. And you see that this picture can be, you can choose as many zeros and as many ones as you want, and this is what is called a bipartite complete graph. You just have two different sets, everything here connected with everything there. And what we see is that for each piece of some color, we need to find a structure like this if you want to realize this colored graph in a Bell scenario. This is another case that's possible, but now we need 3 outcomes. And if we simply give 3 outcomes, this is a good, a reasonable piece that can appear also. And of course, we can repeat the situation. We can now multiply one of those vertices by 2, as we call in graph theory. And something like this is also the same situation as before, but now with 2 different vertices for the 0. And then you continue and you can have every and only the k-partite complete graphs as each colored piece, and this is the complete characterization. But okay, this is going too far. But the beautiful part of discussing like this is, okay, but since we characterize what graphs, what colored graphs correspond to Bell colorings, then there are some that do not correspond. Then there are some colored graphs that we cannot realize in a Bell scenario. So what are then they really telling us? And this is what we call the generalized Bell scenarios. The idea here is quite simple and in the same time quite powerful, that we can insist in the idea of having parts. So we have our Alice and our Bob, but we can allow, so in this case, it's the simplest situation where Alice is working the same way as before. She, in each run, chooses one measurement, perform, and gets the output. But Bob instead can have more than one compatible measurement to perform per round. He essentially has a contextuality scenario to play by himself and to consider this jointly with Alice. And this is the idea of a generalized Bell scenario. So in this simplest case, 2 measurements for Bob with the pair of outcomes, 2 compatible measurements for Bob for each round. And we can just recognize these serif symbols, these vectors y and b, as the novelty in the model. So if before a behavior would be something like this, now we'll just change this b and y for that b and y vectors, for these b and y that are sequence of measurements and sequence of outcomes b. Of course, the idea of a local model should be the same. The only difference is that now here we should consider the sequence of measurements y and the sequence of results b. And the idea is that we can choose where to consider these guys. So previously this question would not appear in the sense that every probability distribution was allowed. But now, since here it's essentially something that appears from a compatibility scenario, it would be very strange to consider in a model things that do not obey even the most basic relation, that is this non-disturbance relation, that for those used to non-signaling in Bell scenarios, it's the similar idea but without parts. So you cannot say about signaling because it's not coming from one part to the other. It's just one result does not disturb the other measurement. Okay? So one question that we liked to focus was, can we have non-locality and local contextuality in the same experiment? So why to make such a question? Essentially because some people had said before that no, that you could not have it. So there was some evidence against, at least for these simplest cases, CHSH and KCBS. So that's what this paper here from 2014 shows, that you can, in the way that they prove, you could not have CHSH and KCBS violation in the same experiment. Some experiment was done to somehow certify that this was the case, that only those correlations would be obtained. See the name Peng Shui here because it will be an interesting coincidence, or a causal coincidence. So here I inverted a little bit who is Alice and who is Bob in our previous discussion. Sorry for that. But here we are considering that Alice is trying to make a KCBS measurement, while Bob has only two incompatible B1 and B2. And then for each round, she could try to see KCBS. And at the same time, when she chooses, for example, A1 and A3 that are incompatible things, she could try to see a violation of case of Bell, of CHSH, together with this B1 and B2. And what they have shown, this is one way of writing KCBS for Alice. This is a way of writing this specific CHSH for A1, A3, B1, B2. And they could show that you have another inequality involving both. And this is just a way of visualizing. Here you see I forget, the umbrella situation. So the five vectors are like this. And they could perform that experiment in, as I said before, the three-path interferometer. So here you have this kind of inception of a three-path interferometer, one after the other, for making the two trichotomic measurements, or the two things that are not exactly trichotomic, but the three-dimensional stuff. And here, just a qubit, just a polarization measurement, and choose which polarization using this wave plate here. And okay, then they could draw this kind of picture saying whenever you have the violation of one, you cannot have the violation of the other. But we could find in our studies of this kind of scenario another different inequality that is a CHSH inequality, but using not only A1 and A3 in this way, but compatible things. So you could use, I will write it here soon, and see that the same Peng Shui comes here in this experiment, because here Rafael was the one that got in contact with Peng Shui to ask, do you have the data from that experiment for us to test if some other situations here? But it would not be effective because we would need some different states instead of the ones that she had already measured. But she said it's not difficult for us to redo it. So that was the point. And here you can see the compatibility structure that we are studying. So back to our notation, Bob is the one with the KCBS. You have this pentagon here for KCBS and two different measurements for Alice, each of them compatible with everything in the Bob part. And the important part here is that we have triangles of compatible things. And this is what they were ignoring when enunciating it is not possible to violate both. They were trying to violate KCBS, that's reasonable, and for CHSH, they were only using A1 and A3 in their example. But we can have something a little bit different, that is this kind of inequality here. So you see that B2, B3, if we go to the plus and minus one outcome thing, each one of them, each BI being a plus or minus thing, this product B2, B3 is also another dichotomic measurement with plus and minus answer. So this is another realization of CHSH that now can be done together with KCBS for Bob, and we could obtain this kind of graph. So you see that here is the boundary for the bound for CHSH. Here is the bound for KCBS, and we have these three experimental points here, 5, 6, and 7, where both of them are violated. So in red here, we have the theoretical results using some parameterized state. So the measurements are always the same because this is the rule of the game for nothing being able in the previous situation. So we have always the same choice of measurements for Alice and Bob. They already defined this. But by changing the state, we can go from a region where you have large violations of KCBS, but no violation at all of CHSH, towards another situation where you have large violations of CHSH, but with no violation of KCBS. But in between, you can have both here. This blue curve is just using what we call NEPA hierarchy to say that quantum could never go beyond them. It's not necessarily true that can reach it, but it's something that we know that can never go beyond. Okay, and no surprise, it's essentially the same experiment. The only change is that now we need to work a little bit better with the choice of states here in order to do all this parameterized curve here. Okay, some referee was complaining, you are showing this just for one scenario, then theoretically we went for many any cycle inequalities together with CHSH. And another interesting thing is that the previous guys had used just this kind of CHSH, and in this case you could not see violation. In the previous discussion, we used this thing here, but of course there is another family of inequalities that you can use that is, instead of B0, also use some pair of compatible measurements for this part. And here you cannot even see the difference, but if you really take a look here, there are two different blue lines. It's one for this family, another for that family. So there is a small difference among them, but really small. And we only have, to the moment, this kind of verified up until 10,000 and conjecture for every n. One guy that has just become a doctor a few months ago say that he has this demonstration, but we still have to check to see if this conjecture was upgraded. And here I'm just remembering that any cycles were completely characterized in this physical review A 12 years ago. So if you want to go further and further, as we play here in the title, there are some disturbing consequences of using other things instead of not this non-disturbance here. So we can do different local models by applying different constraints for these guys. And one thing that we really consider curious, so let us generalize a little bit more. So here we have now in both parts you can have contact this compatibility thing, these vectors. And then one natural question is, does it make any difference to impose local contextuality before or after what I'm calling before and after? Before, I'm calling impose in the model. Just use non-contextual distributions for part A and non-contextual distributions for part B. So see what happens with this local model where everything is non-contextual in each lab. And the after is consider whatever you want here, but then impose that no one in any lab can see non-contextual, can see contextuality. Okay, does it make sense? And the interesting answer for this question is yes, it makes huge difference. In terms of notation, here we are calling local using as ingredients non-contextual behaviors for these things here. And here we are saying, do whatever you want with a local model. So take as general probabilities you want from here. But after this, impose that you can only consider behaviors that are non-contextual in each lab. And those are different stuff. Indeed, this one is smaller than the other. And in that paper, we show explicitly behaviors where you cannot, so they are local. So of course, they cannot violate any generalized Bell inequality. They are non-contextual because we are demanding, so they are locally non-contextual. But even in this sense, they are non-classical because the classical stuff is this one. The classical stuff is when you have local model using non-contextual distributions for each part. So in some sense, there is in these generalized Bell scenarios some non-classicality that is manifest but cannot be interpreted nor as non-locality alone, nor as non-contextuality or contextuality, sorry, that appear in some part. This was quite surprising for us when we discovered. So some concluding remarks. Contextuality and non-locality are key non-classicalities, fundamental in understanding quantum theory. They can come together, and those are possible new paths for applications, quantifications, and foundations. Some surprises come from generalized Bell scenarios. They are much more interesting than a first look would say. We're just beginning and more things will appear in the near future. I'm not sure if so near, but in the future at least. And finally, something that I mentioned here, you can learn in this book that I wrote with Barbara. Indeed, Barbara wrote, and I just helped her in many things. Barbara, I supervised her PhD, and this book we wrote immediately after it. It is really based on the results of her thesis and etc. But it's a very pedagogical one, a good way of entering in this whole thing. And another important advertisement, my department is hiring, so we have openings for positions of, how can I say it?
Concursos, right?
Exactly. It's a concurso in good Portuguese for MS3, that is the name, the new professors here. In these three different areas, of course, new technologies, when they were proposed, the two first examples are AI and quantum technologies. So, of course, people can say that they want to work in other new technologies, no problem, but just to say that at least this position here is really searching for someone that could be a specialist in quantum theory, in quantum information, and things like this. Of course, all the others also you can justify somehow, but this one is really tailored for our community. And finally, this is a Latin American thing, and I have to honor Juan Pablo Paz, who, together with other people, started this idea of the Latin American quantum state. a dream to many that hopefully is being prepared and will never collapse. So, muchas gracias. And more
Okay.
questions, please. Sorry for being so long and for the technical problems here.
Thanks a lot, Marcelo, for the very interesting talk. So, guys, now it's time for questions. As I said, don't be shy, just don't need even to raise the hand, just go. Okay, maybe I can break the ice and start, and then probably people will come back, will come after. So, I mean, we are used to always to think that, let's say, whenever you have a quantum advantage is because you have entanglement. And the idea is that whenever you have entanglement, you are non-classical. Now you are saying that there are sources of non-classical that are nothing to do with entanglement because there are no parties at all. So you have already, how can I say, a killer application like an example of a quantum advantage that you can build with this without requiring any entanglement then.
Yes, yes. So there are some demonstrations of advantage in quantum computing
Hmm.
that only need contextuality. That it's not something that you really need entanglement, but having contextuality, you are already there.
Hmm.
And as well, randomness. You can expand randomness just using contextuality. The violation of non-contextuality inequality is as good as the violation of Bell inequality if you just
Hmm.
want to certify randomness. Of course, with Bell, you can certify in some sense randomness and secrecy in,
Yes,
from one part to another. So it's in
right.
some sense more interesting to communicate and to, but for example, if you really want just to run some Monte Carlo and
Mhm.
you want to certify that you are not biasing your sample because your randomness is not as good as you would like, then some tests that come only from contextuality are enough.
I see. Okay, okay. So, are you involved also in that part, or you focus
No,
your no? Okay. So, do you know
unfortunately not.
somebody? Eh?
Unfortunately
Unfortunately,
not.
yeah.
In
Do you
this
know
case of the,
somebody in Latin America that is working in that part, like making, I say, applications out of this concept that is not what we're used?
okay, good question. I know, but I'm not sure
Maybe this
who
is a question to everybody. I mean, also other people
the audience for
in the
sure.
audience can say if they know. Yeah.
So I can tell you that Secure Quantum is a company that is a joint thing of Chile and Poland,
Hmm.
and they are creating randomness. They are, for example, responsible for the lottery of Concepcion in Chile.
I see.
And their test is not related to Bell non-locality. So
I
um,
see.
I'm not sure if it's fair to say that it's contextuality by itself, but it is something quite close to it. So
I see. Okay. Yeah, I'm checking. Yes, this secure quantum technology. I opened the website. So yeah, there are people. Okay, great. Okay, more questions, more comments, more. Herbert wrote Grangi Laude. Sorry, I'm not sure and I get what you mean.
Universidad de Concepción.
Ah, okay. I see. So
Exactly.
they are involved in these companies. This
Exactly, exactly. Secure Quantum is some
I see.
startup that was born. The
Ah, I
Chilean
see.
part comes from Universidad de
I see.
Concepción,
Interesting.
and the Polish guy is Marcin Pawlowski from
Hmm.
Gdańsk.
So, for instance, do you think we can, let's say, involve one of the persons in the company from the Chilean side for a talk? Do you think it
For
could be a
sure, for
good idea?
sure. Hmm.
So Herbert,
If you
apparently you have.
want just the company part, they have a fantastic saleswoman. They have the
Repeat.
CEO. But I'm just joking. If you want just the selling part, you can invite the
Mhm.
CEO and she will convince you that the
Oh,
product is very good.
okay, but
But
I
if you
mean,
want the scientist part,
we're not gonna buy their stocks. So it would be nice
exactly,
to learn also something about the physics, right?
exactly. If
So
you want the scientific part, one of them is Stephen Walburn, the
Stephen
other
Wall.
is
Okay,
Gustavo Lima. Yes.
okay.
So it's
So
a
great.
Chilean but very Brazilian thing. And in the sense
Hmm.
that both of them are doctors at Brazilian
Hmm.
Institute. So both of them are doctors from UFMG, where I worked
Ah,
before.
in Minas Gerais. I
Minas
see. I
Gerais,
see.
exactly.
I see. Interesting.
And now, so
Mhm.
Gustavo, after some postdocs, went to Concepcion and is established there for 20 years or more.
Mhm.
And Steve made a big part of his career at UFRJ, in Rio de Janeiro.
I see.
And after this, in the previous Brazilian government, he moved to Chile and
To Chile.
is
I
very
see.
happy now there.
Okay. Somebody wants to ask more or to comment or.
Oh, just to answer from my part, when we started this thing of generalized
Mhm.
Bell scenarios and etc., Lucas, that is the guy, the master student that nowadays is in Paris for the PhD,
Mhm.
his project, his master project, the central question was related to applications,
Mhm.
and we would really love to have some, so this idea of using different resources for different tasks.
Mhm.
And our guess that was only partially confirmed is that we could use this kind of non-classicality that has to do with both at the same time for parallel quantum computing, for the distributed, not parallel, the
I
idea
see.
that you use non-locality for communication and
Mhm.
contextuality for computing, then distributed quantum computing would be the perfect scenario for
I
using
see. I
resources
see.
from there.
Yeah, sounds reasonable because you have the non-local part between the various nodes and you have the local part within the node. Yeah, I totally agree.
Exactly. But we
But
could not really
yeah,
have a killing example that,
mhm.
okay, here is the protocol
Yeah,
that without these you can't do, or
mhm.
how much of this resource you need to involve
Mhm.
in obtaining these performance or quantum advantages and etc.
I
So
see.
there's really some partial thing that possibly in the future we
Yeah.
can really find.
And
Do we have anyone else in the room?
yes, please.
People so silent now.
Okay, so maybe they are shy, but anyway, so let me reiterate. We want we want to hear something from you also at the level of what you want to hear from other speakers. So please send us suggestions about people that are A, good, and B, are willing to participate and to give a talk. Maybe next time will be November, and maybe we can try to now make a favor to our experimentalist part of the community, so we can look for an experimentalist. So
But
please.
you saw that I mentioned an experiment, huh? Or
Exactly.
two even.
Yeah. No. Yeah, but okay. Let's say I can imagine. Of course, I'm not in the other side, but I can imagine that probably they want to see some more real experiments. So please send us names. Otherwise, I will try my best to find an experimentalist. But yeah, if I get suggestions, I'm more than happy. So probably we can stop here. I thanks everybody and I will probably try to send an announcement in the next few days, but the hope is that around the end of November, we will have the next webinar. So yeah, thank you very much, guys, for being present, and see you next time.
No one else
Bye-bye.
will open camera and say hello?
Say again? Ah, yeah, please. No, they are shy.
But
Okay.
okay, they are shy, no problem. But good to see you
Okay,
all.
yeah.
Hello, Hebeche. Hello, Amado.
Bye-bye, guys. See you next time.
Bye.
Yeah. Thanks.